Hello everyone, my name is Samir SELLAMI. I'm a doctor in computer science from the University of Constantine to Algeria and a researcher at Elite Lab in Toulouse, France. Today I'm going to present my work entitled Knowledge Graph for efficient bridging between business data with large-scale web data. My presentation is organized as the following. I will begin by presenting the context and the motivation behind our work. In the light of that, we show the limitation of some existing work and point out our research focus and goal. Next, we present our proposed approach and take time to detail our three contributions named respectively MITSAM-I, KGMAP, and KFS. Then we demonstrate an evaluation of our prototype implementation through a use case of data integration in a commercial enterprise scenario. Then we present an experimental study to test the effectiveness of our contribution and compare them with those of state-of-art integration approach. Finally, we finish the talk by a conclusion and future works. Today, the world is making a digital copy of itself. According to Oracle Big Data, 19% of the world's data has been created only in the last 2 years. That's a really huge amount of information. But how can we make use of this information? While the volume of this data are increasing, this growth far exceeds the ability of users and businesses to effectively use it. 6 out of 10 companies have more data than they effectively use. And company leaders believe that their organizations are losing revenue due to their inability to master the available information. So the challenges for both users and businesses are how to access this data, how to gather and integrate this data from different sources, and how to use it effectively. Almost all of this data is on the web somehow, and on this web we find different types of data. Structured data in form of RDF or legacy relational databases, semi-structured hierarchical data in XML or JSON exchange format behind web APIs, and unstructured data generated mainly by social network in form of text, images, or videos. In our work, we are interested in structured and semi-structured data, mainly structured relational and linked data, and semi-structured data generated by social network web APIs. However, this data variety on the web leads to data heterogeneity problems. Heterogeneity conflicts can be classified to technical, syntactic, schematic, and semantic conflict. Technical heterogeneity includes all the differences in the mean of data access, for example, different communication protocol or query languages. Syntactic heterogeneity is caused by the use of different models, for example, relational, RDF, or XML model. Schematic heterogeneity is the result of the use of different structure or schema to model the same reality, and the semantic heterogeneity is caused by different meaning and interpretation of data in different contexts, for example, synonyms, or also confusion conflicts. So to achieve data interoperability, the issue posed by data heterogeneity need to be addressed. Sir Tim Berners-Lee, the father of the web, and the semantic web community did a great job. They proposed the semantic web stack you see here on the right and set of 4 principles for publishing data on the web. The first principle is to use URIs to identify things inside the data. The second principle is to use HTTP URIs so that people or machine can look up those names. Then when a URI is looked up, to return a machine understandable description in RDF format. And finally, to include links to other related things. The application of the linked data principles has led to the birth of the web of data and to the rise of the knowledge graph. The picture you see on the background represents the linked Open Data Cloud, and within its center you see the DBpedia knowledge graph. After that, we have seen emerging survival knowledge graph project, open knowledge graph such as Wikidata and Yahoo, the Google knowledge graph, Facebook Open Graph, and many others. So this was the context. Let's now move to our research focus and goal. So let me explain the situation. So we have in one side a lot of heterogeneous data sources, and in another side we have users and experts inside the enterprise who want to be able to access the data and ask business questions. They want to generate reports and do business intelligence stuff. But in the middle there is this gigantic conceptualization gap. So the question is, how do you bridge the conceptual gap between the enterprise and the data? The shorter answer, as you guess, is using a knowledge graph, but unfortunately not all enterprises have the necessary resource like Google or Facebook to build their own knowledge graph. So longer answer would be that enterprise need methodologies for knowledge graph creation, collecting and analyzing data source, then extracting their metadata. After, they could implement information mapping and query tools. This slide shows an example of a knowledge graph and two entities, a resource in DBpedia and a row in Oracle Relational Database about the company Dell. So our intuition would be to automatically detect if there is any semantic equivalence between these two entities using some kind of similarity measure, then establish a mapping to a knowledge graph concept, for example DBU organization, to facilitate data integration and then data exploration. LDIF and MinutePlus are two recent systems for data integration. LDIF is a materialized framework to integrate triple-based datasets, and MinutePlus employs a virtual molecular RDF approach to integrate semi-structured data. The problem with these works is that they focus mainly on RDF or in converting data source to RDF data model. Also, existing relational to RDF mapping language or RML, which is by the way a W3C standard, support only structured data and the mapping are generally manual. On the other side, ontology matching techniques support only OWL and RDFS schema and take as an input only to ontologies. So this leads us to ask the following search question: how can a knowledge graph and semantic similarity measure facilitate the mapping process of entity collected from heterogeneous data sources? In the side of exploration system, hybrid search engines such as Google and Yahoo perform a more or less federated search. However, these search engines are not federated in the sense that at the time of the search, various decentralized sources are consulted. Rather, they create a content or integrate a content into a very large search index. In addition, they do not allow to browse all the segments of the web, such as the web of data or social web APIs. On the other hand, multifaceted search interfaces such as SAMFacet and LDR are applied mainly for RDF data. They are based on the Sparkle query language, which is too complex for ordinary users. So this leads us to ask the following search question: is it possible to search and explore integrated data, for example relational, social and linked data, with a simple and user-friendly interface? Therefore, our goal is to design a system that integrates internal enterprise data with large-scale social and linked data, that first manages the heterogeneity of data source in terms of their data model, data types, and access mechanisms. Second, interconnect the similar entity by exploring semantic similarity measures. And finally, to build a user-friendly exploration interface for non-expert users to hide the complexity of writing queries. So after showing the search problem and goal, let's now move to our proposed approach. Our work provides both theoretical and practical contribution to the semantic integration of heterogeneous data. So these slides show the complementarity of our three proposed contributions. First, MidSemi or middleware for semantic integration, which provides a global framework for a knowledge graph creation and source metadata extraction. Second, KGMap or knowledge graph mapping model, which presents a matching approach that allows establishing a mapping between the knowledge graph schema and the source metadata. And finally, KFS, or Keyword-Based Faceted Search over Integrated Data, which presents a semantic search engine that ensures the rewriting of user query and the exploration of integrated data. Let's begin with MidSAM-I. So MidSAM-I architecture consists of 3 layers. A presentation layer that essentially consists of a multifaceted user interface that allows a keyword-based search and exploration of integrated data. A schema and metadata layer configured by an expert and presents the logic of the mediator. And data access layer that consists of different wrapper models that are responsible for extracting data from different data sources. Note here that the knowledge graph is a central element in our architecture, and it acts as a vocabulary used as a common language between these different layers. So first of all, our approach consists of the curation of the knowledge graph schema. In this process, we suggest to reuse and extend existing well-known vocabularies such as FOF, DBU, and schema.org. Then we maintain the knowledge graph schema in an internal representation model. So this model consists of entities you see here: vocabulary, concept, attributes, and relation. Second, we extract the metadata of source in description model of source. So this model captures the metadata at 2 levels. The first level holds general metadata about the source type and the access mechanisms. The second level captures detailed metadata about the description of its schema element, for example, tables and columns names for relational databases. In the middle, KGMap consists of a bridging mechanism between these 2 models. So we propose to link the source metadata with the knowledge graph schema concept, relation, and attributes. This with using 3 types of concepts: mapping for concept or concept map, mapping for attribute or attribute map, and mapping for relation or relation map. So for concept or concept map, we have the following cases. The first case is a direct mapping between a table in a relational database to a concept in the knowledge graph. The second case is a direct mapping between a concept in a linked data source to a concept in the knowledge graph. The third case is a direct mapping between an object in a web API to a concept in the knowledge graph. And the fourth case, when the mapping is indirect, we define a SQL, Sparkle, HTTP view to a concept in the knowledge graph. For attribute or attribute map, the first case is a direct mapping between a column in a relational database to an attribute in the knowledge graph. The second case is a direct mapping between an attribute in a linked data source to an attribute in a knowledge graph. And in the third case, a direct mapping between a parameter in web API to an attribute in the knowledge graph. Note that here we use a different conversion function to address different data value heterogeneity. So based on the KGMap model, we apply an automatic algorithm for identifying direct mapping pair. So the input of our algorithm are the knowledge graph schema, the source metadata and threshold, and the output are the mapping pair. So first, the algorithm traverses the knowledge graph schema element, and then depending on the source type, the algorithm traverses the source metadata element, then calculate a semantic similarity seam between them. So if the semantic similarity seam is greater than threshold, the element pair is identified as a direct mapping and maintained in the knowledge graph model. So once the mapping between the semantically equivalent entities are calculated, we pass now to our rewriting query process. So first, the interface accepts a simple keyword as an input to allow non-expert user to perform simple queries and benefit from the service provided. Then KFS applies a named entity recognition on the keyword entered by categorizing them into classes of the knowledge graph. For example, if the user enters the keyword of the footballer named Riyad Mahrez, the classifier determines that it's a kind of a person. So until now, the system has the keyword that will be recognized in one or more concepts of the knowledge graph and the mapping information in the mapping schema. So using this information, the query writing engine determines the relevant sources and proceed to the creation of different queries. Either a SQL query on a relational database, a Sparkle query on a linked data source, or HTTP request on social web APIs. KFS sends the reformulated query to the related wrapper, and the wrapper extracts data from the related data source. KFS repeats these steps for all relevant data sources. If we take the example of the footballer Riyad Mahrez, the concept obtained after classification is person, so this concept corresponds to the customer table in the CRM database and to the object user in the Facebook web API. Therefore, the query writing engine generates two queries, a SQL query that will be executed on the CRM database and an HTTP request that will be executed on Facebook web API. KFS converts the data if there is any heterogeneous attribute value, for example, different format of dates. Then, the system combines data by applying a simple data fusion strategy of type union. Finally, KFS presents the final answer to the user on a multifaceted navigation interface. So we have implemented this process in an algorithm that runs automatically in order to make the integration completely transparent to the user. So let's move now to the experimentation part. We used the .NET platform to implement our approach. We used C# and JavaScript languages in Visual Studio environment and SQL Server database to implement the mapping schema. As a runtime environment, we used Windows 10 machine with an Intel E5 core processor and 4 GB of RAM. And the implementation code source is publicly available. You just have to scan the QR code to access this repository. This slide depicts the graphical user interface of the mapping information module. The navigation bar shows the concepts and attributes mapping, each grouped in subcategories. The detail view shows the knowledge graph and the data source element in hierarchical tree views and illustrate a mapping patterns with a relatedness function or measure between the elements. Using the ribbon menu, an expert can add, delete, or validate the mapping information patterns. For user sides, KFS web interface allows introducing a simple keyword-based query. So the main interface includes search area and a resource or entity selector. For example, for the keyword Riyad Mahrez, the integration results are visualized on a multifaceted navigation interface which has several views. A navigation and status bar on the left, a result container in the middle with different source provenance information, like you see here, and views and settings bars on the top. We evaluated our approach regarding the following aspects. First, the impact of applying different similarity measures to KGMap. Then the efficiency of KGMap compared to related state of our tools. And finally, we evaluated how user-friendly is KFS web interface. To achieve that, we created a ground truth knowledge graph schema extracted from 3 online vocabulary, FOF, DBU, and schema.org. We used 3 heterogeneous data sources, Microsoft Relational Database or AdventureWorks Relational Database, RDF datasets, and Facebook Web API. Then we manually generate both concept and attribute mapping for these 3 heterogeneous data sources. We assessed KGMap with 2 different similarity measures. First is the Jaro-Winkler similarity, which is a string-based similarity algorithm which employs a mixture of string and set similarities. The second measure is the UMBC similarity, which is a semantic-based tool constructed by mixing latent semantic analysis and WordNet knowledge. And the gold standard table in the bottom shows additional statistics on the experimental configuration. we computed precision, recall, and F-measure according to the gold standard. Jar-Winkler demonstrates a lower performance as its algorithm relies just on the syntax of the string. On the other hand, UMBC shows better performance because it concentrates on the semantic of the word and not on its lexical category. Nevertheless, the performance depends on the threshold parameter, and UMBC was capable of maintaining stable quality on threshold up to 0.6. So we found that UMBC is a typical similarity measurement for our approach, and we adopt it. The second table reports the evaluation of KGMap compared with LDIF and MINAT+. The highest values are highlighted in bold. The result indicates high precision, which means only true positives were identified. LDIF recall remained stable because it was configured using the Slick tool to generate only all same as mapping for the DPpedia dataset, since this approach supports only RDF data. For MINAT+ and KGMap, the recall decreased with a higher threshold, and KGMap was slightly better compared to MINAT+. We explained that by the ability of KGMap model to cover not only web datasets such as DPpedia and Facebook, but also relational data models like the SELLAMI database. For the KFS interface, we conducted a formative evaluation to assess its usability. So the evaluation instrument consists of 4 tasks, for example, to find information about a famous person that the participant knows. We selected 5 participants with average experience in software development, so the participants were 3 males and 2 females between the ages of 25 to 35 years old. Then we calculated the task completion rate using the following mathematical formula. So the percentage of successfully completed task, or SCT, divided by the total number of tasks per scenario, or the TNT. On the right, you see here the result of the usability of our KFS interface compared to SAMFACET and LDR interfaces. The user performed the 4 tasks at once per system with 5 minutes break in between. The results show that KFS performs within the expected parameters, with many users achieving a per task completion rate at least of 16%. It was also the only interface that achieved a rate in task 4, confirming an increase in visibility over the older systems. LDR came in the second in terms of performance, better than our KFS interface in task 1 and 3, and SAMFACET performed poorly with an efficiency rate below 15%. That brings me to the last part of our presentation. So in summary, we proposed first NCASAM, a flexible and a modular middleware architecture to bridge between a diverse heterogeneous data model. Then we present a new mapping model and an automatic algorithm for detecting direct mapping pair, which is KGMap model. After, we explained the KFS process, a semantic search engine for query writing and exploration of integrated data. And finally, the evaluation results showed the KGMap effectiveness and the KFS faceted interface usability. As future work, we are planning to add support for new mapping cases and automatic detection of indirect mappings, add support for text documents by employing deep learning and word embedding techniques, test the scalability of our approach and adapt it to other fields such as IoT, and finally to allow recommendation and serendipity. Serendipity here is when the user does not know what to look for, or he does not have a particular keyword in his mind, and in this context the interface must be able to guide him in his exploratory search and propose to him various possibilities. So this was all what I have to say in this presentation. So thank you for your attention, and your questions are welcome.